mid-air ultrasound technology offers new possibilities for delivering haptic feedback from a distance without requiring physical contact. So haptic designers can create mid-air ultrasound patterns, or tactons, for contactless user interactions in various applications. Prior studies have investigated various applications of the technology, such as in public displays, automotive UIs, and virtual reality. These applications use ultrasound tactons to convey information or emotions to users. To convey information in an application, tactons must be easy to distinguish for users. One common design process is designing an initial tacton set and then running user studies to identify a subset of distinguishable tactons. More specifically, a designer may create tactons by systematically varying the parameters of a haptic signal, or create tactons to remind users of metaphors such as heartbeat. Then, the designers run user studies with the initial tacton set to derive its perceptual dissimilarity space and select the most distinguishable subset of tactons for an application. For mechanical vibrations, haptic designers can use extensive research on the perceptual similarity of mechanical tactons. But little is known about the distinguishability of mid-air ultrasound tactons. To inform design of mid-air ultrasound tactons, we ask, which temporal parameters can help create distinguishable mid-air ultrasound tactons? Also, to test if designers can use their knowledge on mechanical tactons for ultrasound design, we ask a second question: how does the distinguishability of ultrasound tactons differ from mechanical tactons with corresponding temporal parameters? We designed and ran 5 studies with 72 participants to evaluate the efficacy of temporal parameters for ultrasound tactons. We placed the mid-air ultrasound device on a table in front of the participants and collected their responses with a graphical user interface. In Study 1, we investigated the discrimination thresholds for infrequency of mid-air ultrasound vibrations. Next, we created 4 sets of mid-air ultrasound tactons and estimated their perceptual dissimilarities based on user pairwise ratings in studies 2 to 5. We selected these 4 sets from the mechanical tacton literature that reported the similarity rating data and the perceptual spaces. Across the 5 studies, we kept the spatiotemporal parameters constant, as this work focused on the temporal parameters of ultrasonic mid-air haptics. Thus, we maintained the same trajectory, size, and drawing speed of the focal point, as well as the height from the device, across studies 1 to 5. Study 1 investigated discrimination thresholds for infrequencies of 30 Hz, 80 Hz, and 210 Hz. The results showed infrequency JNDs of 47%, 77%, and identified significant differences in JNDs between 30 Hz and 80 Hz, as well as between 30 Hz and 210 Hz. Our infrequency JND results were higher than the frequency JND for mechanical vibrations, which was around 15%, 30%. Subsequent studies 2 to 5 examined the perceptual distinguishability for the 4 sets of ultrasound tactons. We selected these tacton sets from the mechanical tacton literature considering various design approaches and design parameters. We then created corresponding ultrasound tactons that vary on parameters of sinusoids, rhythms, and complex waveforms. We analyzed their perceptual spaces and identified salient temporal parameters influencing perceptual dissimilarity. For example, rhythm can greatly influence the perceptual spaces of ultrasound tactons. It served as the primary perceptual dimension for complex ultrasound tactons. Moreover, The Tacton set varied by rhythm showed the highest correlation between the dissimilarities of ultrasound and dissimilarities of mechanical tactons, suggesting rhythm as a key parameter for creating distinguishable tactons in both contact-based and contactless technologies. Even the lowest correlation in similarity ratings between the ultrasound and mechanical tactons among the 4 tacton sets was higher than 0.6, indicating that their relationships maintained high correspondences across the tacton sets. These results suggest that the temporal factors played a dominant role in mid-air ultrasound tacton perception. Based on the results of studies 1 to 5, we present 6 guidelines for designing distinguishable ultrasound tactons. The detailed guidelines can be found in our paper. We hope our findings help designers create perceptually salient tactons for contactless interactions. Thank you for watching our presentation, and feel free to reach out with any questions you may have.